Hi, this video is focused on inelastic collisions. Okay, I got the track set up with the cars the basic way the directions indicate, and it's pretty level on the track. You see the bubble right there, and you see this is the level track. This is where the two tracks meet right here, and this is my ramp with the wooden block that I can raise and lower the ramp to see what height works the best. The blue car is going to come down the ramp and crash into the red car, and it says in the directions right here to find the best height that seems to work well for the timing is what it means after the collision occurs, to time it. So after they collide, we're going to time the two cars are going to stick together from the Velcro. We're going to time how long it takes for them to move all the way down to the end of the track there, and see if that agrees with the ideal inelastic collisions. You can see when they collide here, boom, they stick together and they continue moving with very low friction. Excuse me. So that's the idea again, that these cars are going to have very minor friction that can cause any significant deviations from the ideal equation results. That's what we're putting to the test, at least. Now, it says to start just from the directions again. It says to place the hit car. This red one is going to be the hit car. It's going to get hit by the blue one. And it says to start them about start the red car about half a meter down from the end of the ramp. So here's the end of the ramp right here, and this is just from a prior experimenting that this was found that if you put the hit car about half a meter down, that's usually a pretty good distance for the blue car to come down the ramp and come onto a level surface here, hit the red car with enough momentum that it will roll off the end of the track fast enough that we can not lose any significant energy or speed from friction, and it's still not too short of a distance that it is too difficult to measure the time for the cars to travel that distance. So that's kind of the back and forth we have to experiment with a little bit to see how fast we can reasonably measure an accurate time for the cars to go through this small distance here. Okay. Good on the consistency and the amount of time it takes. So just to give you guys an idea, again, I'm putting this right at the same starting point from the end of the ramp here to where this collision occurs, right at 0.5 meters or 50 centimeters from the end to here. And then we're going to measure, of course, this distance from here there to see how far it travels after the collision. Now, what I was timing, of course, was how long that takes to see if it's reasonable to get consistent times during that period. So here it goes. I'm going to put it on the end up here. I know you can't see all the way to the end, but I'm going to start it up here, and then you guys can see how long it takes. Okay, so here it comes. Ready? Okay, so I'm getting pretty consistent times, and that's about how long you're going to have for each trial once the experiment starts. That was just a test run right there. Okay, this next part is just measuring the height through which the ramp car is going to be traveling due to gravity, and from this height measurement you can calculate its gravitational potential energy. Now this height measurement is just like the home lab experiment that you did in which you had to measure the height of the ramp above. Well, it's practically just like it. So all you need to do, and again, this is just like the home lab, except for on the home lab, the only difference is you had to measure, at the end of the car. In this one, we're measuring at the center of mass of the car. At least the assumed center of mass is in the center of the car, and that way we should get the most precise change in its overall mass, or its average change in its height for the mass. Anyhow, you got to make this measurement right here, and I will zoom in a little bit. And this is from the surface of the table just up to the bottom of the track right here. That's the height change through which the car is going to be moving, and that will give us the gravitational potential energy converted to the kinetic energy of this car, and that's of course dealing with conservation of energy, and that's how we can figure out the speed that this car is going to be moving when it hits the red car. Okay, so let me zoom in on this a little bit for you. Oops, this is going to be a little bit hard to get with the camera just right. Okay, so hopefully no parallax errors are causing too much issue. So again, we're going from the bottom of the table up to the bottom of the track right here. So you need to get right where it comes across to the bottom edge of the track, and we need 3 significant figures. Well, we can actually estimate to a 3rd significant figure here. So you can make that measurement, I'm making that same measurement, and we should agree on our measurement, plus or minus a few hundredths of a centimeter actually. Okay, now this is extra here to make sure I start the car from the precise same position each time, and it's convenient. I put this little weight right here, 100-gram mass right here to stop it. Then whenever I want to start it, I'm just going to pick up the mass, and right under there, I don't know if you can see that, I drew a nice pencil outline. You can barely see it. Nice pencil outline where I'm going to put the mass each time, so that I know that it's stopping the car each time, and that way it's easy to be consistent with the exact height that I'm starting it at. Make sure it's lined up on the wheels. Track right there, and then I'll just remove it, bing, and I'll start the car down the ramp. I'm always checking to make sure the tracks are aligned, the grooves of the track where the ramp meets the track, the flat level track, nice and aligned. Alright, so next we need to measure the distance that the cars travel after the collision. So I'm going to start the hit car every time right here at about, like I said earlier, 50 centimeters. And that will correspond on the track to this mark right here for the front nose of the red car. So every time I'm going to start it right here before the collision, and we just need to measure the distance from the nose of the car to the end of the track here. So let's see what that comes out to be. Let's get this here. I'm going to line this up with the mark right there, right about there, lined up. Okay, and then we'll see how far down the track, how far it travels. See if we can get this measurement. It's 50 something centimeters. So here we go. Sorry about all the jiggling camera here. So you should be able to get easy 3 significant figures on this measurement. And 3 is good enough. If you really wanted to, you could estimate a 4th. Alright. So So far we've done delta H and D, and you write your results on the data sheet here to turn in. Now it's up to you guys to calculate the speed. The formula is given in the handout here. This is the initial speed of the collision, and again we get that from conservation of energy, with the energy, the potential energy of the blue car getting converted to kinetic energy and solving for the speed of it. Anyhow, the final speed then is going to be found from conservation of momentum equation, and then you can simply get the predicted time to travel this distance that we just measured using that final speed calculated from conservation of momentum after the inelastic collision. All that's really left for this video mainly is for you guys to get the experimental times after the collision, and that's what we'll do now. Well, just real quick first, for those of you who might not have your lab sheets handy whenever you're watching this video, or if you don't have these particular lab sheets, then this is the equation from conservation of energy right here. You use the definition of kinetic energy is 1/2 mv squared, and you set it equal to the gravitational energy here and solve for v, and that gives us speed after the car goes through this change in height that we just measured. Okay, so that's the initial speed before the collision, and then the equation calculate the speed after the collision using conservation of momentum. The resulting equation that we need is just right here, where these masses are the masses of the cars. Well, this is going to be the mass of the blue car, the mass of the red car, and the sum of their masses in the denominator here, so we can use this equation straight out to calculate the final speed after the collision, and then of course the time predicted is just going to be the distance divided by that final speed for this speed. Okay, you guys ready? Now I did check that test run, and I made sure that I could time the video result for the cars going to the end of the track, and it came out the same as the time whenever I just did it here in person, so there's no issues with the video timing being more difficult, it seems, than being here in person. So we're about to start the time trial, so on your data sheet there's 5 blanks. I may do more than that depending on how consistent it seems, and we just need to do this run 5 times to see what the times come out to be from the experiment. Okay, so let's get started. Here's the first one. Now you guys are going to have to time these, and you know, in past videos I just did all the timing myself, and you guys didn't have to actually time it in the video. For some odd reason it didn't seem as practical in the past videos, but this one is small enough, it should be easy enough that you can do this from watching the video and not get too frustrated or bored with how difficult it is. Okay? Okay, so let's do the first trial. Ready? I have to go out of the screen here multiple times, or reach out of the screen to get the blue car started. So here we go. Ready? Here it comes. Alright, that was the first trial. Slightly shorter than the test fire. I might do my reaction time slightly shorter. Alright. Realign the car, starting position. Put this one over here. 100-gram mass. Make sure I start this one in the exact same position. Okay, here we go. Okay, that was pretty spot on with the trial run. Okay, hope this is working for you. So trial number 3 here. Realign. Okay. find over here. Okay, ready? Nope. Oh, I kind of messed up on my timing here. That was a long one for me, but that was because of my mess up with the timer. I'm definitely going to have to do another one. You guys might have got that better on the video than I did here. Alright? Yep. Okay. Car. Okay. Go. Alright, here it comes. Now, I timed that one good. So, that was trial number 4. Me is just trial number 3 because I messed up that third one. Good morning. Yep. Alright. Stopwatch ready here. The spring gun shot off. That was awesome. It didn't shoot off until it hit the end of the track though, and it was because it was like this. I think nothing shot should hit the spring gun. But the timing seemed to be spot on. Good. Where I'll go in here. Cards up. What's ready? That one was a good one for me. Okay, I got 5 good times, and I definitely had one outlier for my bad reaction time and fumbling the stopwatch here. But I got 5 pretty darn consistent runs, so I don't even think I need to do another one. I know it's great fun, but I'm happy with these results. That's good enough for now. So that's the record for the shortest video yet. Now, I did think about getting you guys to do this one at home, sticking a little sticky Velcro on the end of your Hot Wheels cars, but it just didn't work very well, so I did it here instead, because this has the track with the nice grooves for the wheels to keep the cars moving straight before and after the collision, and it didn't work for the Hot Wheels. There you have it. Hope you enjoyed this short little video, and you got your data, and you can do the calculations, and hopefully we'll get good results agreeing with the predictions from the theory. Thanks for watching.